everyone! Today our presentation topic is the characterization of copper India gallium sulfide. Here is the outline of today's talk. First, we will introduce the background and importance of copper India gallium sulfide. Then we will present several characterization methods, including morphology, composition, and surface analysis. Finally, we will summarize the outcomes we expect from this work. Copper India gallium sulfide is a semiconductor composed of copper, indium, gallium, and sulfur, mainly used in thin film solar cells. It has many advantages. The raw materials are relatively cheap. The band gap is tunable. The absorption coefficient is very high, and the preparation process is relatively simple, which allows for high efficiency. It can be fabricated into very thin layers and deposited on glass, metal, or even plastic, making it lightweight and flexible, ideal for building integrated photovoltaics. However, it also faces challenges: poor charge separation, deep level defects, a narrow processing window, and difficulty scaling up to industry. These are the key issues we aim to study and optimize through characterization. For morphology characterization, we mainly use three techniques. First, scanning electron microscopy, or SEM, provides a rapid and intuitive assessment of film quality. Second, atomic force microscopy, or AFM, gives us three-dimensional surface topography with nanometer resolution and roughness measurement. Third, transmission electron microscopy, or TEM, offers high-resolution imaging to observe phase interfaces and nanostructures. Together, these methods cover both the surface and internal structure at different resolutions. For composition analysis, we use three tools. Ultraviolet visible spectroscopy helps us in bandgap engineering, for example by tuning the GOT-S ratio, and it also evaluates optical quality and stability. X-ray diffraction, or XRD, provides long-range ordering information and helps determine whether secondary phases are present. Raman spectroscopy is more sensitive to secondary phases, disorders, and strains, making it a good complement to XRD. For surface analysis, we use X-ray photoelectron spectroscopy, or XPS. It allows us to determine the valence states of elements, such as distinguishing copper-1 from copper-2, and to detect surface oxides. This is very important for understanding interface properties and device stability. Finally, here are the expected outcomes. First, we aim to build a comprehensive understanding of copper India gallium sulfide from multiple scales, from macro to micro, from local to surface. Second, we wanted to establish clear relationships between fabrication processes and material properties, and identify the key factors that influence device performance. Third, with this come-driven approach, we hope to fundamentally optimize processes to improve device efficiency and stability. That concludes our characterization proposal. Thank you for listening.